Cool. Let me just share my screen. Okay, can you guys see this?
Yep.
Okay, cool. Yeah, so I'm Alex. I moved to San Diego back in March or so. Ian and I started attending SDML. We started, we did the Vesuvius stuff with Ryan and Ted over the summer, and we've sort of been getting increasingly involved in this community. My personal background is I studied neuroscience in undergrad, got interested in machine learning and data science. And so then I went to Johns Hopkins. I got a degree in biomedical engineering with a data science concentration. And so then I worked as a machine learning engineer at this company that did defense contracts in Maryland. And then I moved here. Now I'm working at a company that does machine learning for drug discovery. So the general idea is to build a bunch of models that can right now predict toxicity in different what's called oligonucleotides, which are little RNAs that can edit molecules easily, with the goal of quickly figuring out which ones are toxic and which ones aren't. And so I've also sort of, in the past 4-ish months, I'd say, I've sort of gotten a little bit interested in this subject area of knowledge editing. And so I figured it was, a good excuse to do a bunch of literature review and research to give a talk. So, so the idea with knowledge editing is, in the last few years, there have been, sort of increasingly big models that get trained, right? And so a lot of what, people do in practice these days is to just take one of these giant pre-trained models and, and fine tune it for their own purposes, or, just sort of use the default one that's been pre-trained because, they're trained on, 100 GPUs for, 3 months or whatever, right? And that's cool because they work really well, right? You look at ChatGPT is the obvious one, but if you go onto Hugging Face, there's a gazillion big models that you can just use and fine tune. The problem is that because that's sort of the era we live in now, it's very hard to make a model sort of suited to your own needs, and two, it's hard to do research on these big models, because if you're a lab, you need $1 million to train something new, right? And so the only people who can really make real changes to these things is these giant research groups with a gazillion amount of money that they got from their partnerships with Microsoft or Meta or whatever. And so in the past few years, there's been sort of this focus on, okay, instead of doing training runs, and instead of even doing any back propagation at all, where you need to spend a ton of money on GPUs, what kinds of ways exist out there to just edit the weight space directly in inference time? And so that's sort of hard to do, because the whole point of back propagation is to edit the weight space in ways that you want. But it turns out that there's some interesting ways to do it. Another sort of big motivation for this area of research has been the whole group focusing on AI safety. Anthropic kind of leads the charge on that, but sort of very related to this is the idea of okay, where does knowledge live in these big pre-trained models, right? So can you pick apart mechanistically, which layers are responsible for storing knowledge, how they store that knowledge, how does that work? Because clearly, if you type into GPT-4, what's that big building in the middle of Seattle that's super famous for tourism? It'll tell you it's the Space Needle. And so clearly somewhere that knowledge exists. And so a big question is like, how is that stored? I think I'm sort of personally interested in that as well, because, I think I got really interested in this from the neuroscience perspective a while ago, right? How are memories stored in the brain? What are the physical mechanisms by which you can do that? I don't think neuroscience has an answer to that, but I think this is sort of an analogous question in language models and and more generally sort of all of these big pre-trained models that I think it's a very interesting question. So specifically, you want to be able to pinpoint the set of weights or the functions of sets of weights that are responsible for holding knowledge. And then the other thing that you want to do is you want to be able to apply edits to that knowledge at inference time. So those are sort of the two big goals of this cluster of research. And so there's a lot of ideas that people have. Before I run through these, I think it really helps to get a sense of who is doing research and where. So Anthropic, sort of, like I said, is sort of a big player in this area. Their head of interpretability started this mechanistic interpretability transformers circuits thing. They also did the kind of an equivalent thing for convolutional neural networks. And so, unfortunately, I didn't include that in these slides, but I'm going to link the paper to everybody to check out after, because I think that's sort of a really major player in this area. And then there's also a lot of university groups that are sort of doing this. So the Allen Institute for Artificial Intelligence in Seattle is sort of very focused on language models, and they have an interpretability group along with actually a group at Technion University and Tel Aviv University in Israel. They do a lot of publishing together on understanding knowledge localization. Another sort of related group is David Bau's group at Northeastern University in Boston. They kind of do the same thing. They're connected with Jacob Andreas at MIT. And then Chris Manning at Stanford has been working for many years on sort of similar problems to this in language models. He's a computational linguist by trade. And then also there's sort of online groups that have been working on this problem. So Anthropic is sort of connected to a lot of these, but EleutherAI has a whole area on their Discord devoted to interpretability, and so I mentioned one of their papers here. They're sort of related to Jacob Steinhardt at UC Berkeley, and his group has been doing a lot of sort of like very mathematically dense explorations in this area. So the general ideas that we'll explore here. In diffusion models, you can there's a paper that we'll look at first where in diffusion models you can find a semantic latent space, and then you can essentially run PCA on that space, decompose into sort of orthogonal directions, and it turns out that those directions are interpretable. Another thing that we'll look at is that transformers, so language models have an embedding matrix that they generally start with before all of those embeddings get run through all of the transformer layers and feed forward layers, and those embeddings, it turns out that if you have a lot of them use the same initial embedding matrix, and so it turns out that there's a common subspace if a model is using that embedding matrix that you can project into, and so you can compare multiple models by doing that. Another thing that and so that's been the Tel Aviv group with the Allen Institute for AI did that. David Bao's group at Northeastern did the knowledge localization stuff. So they ran this interesting ablation study where they sort of added noise to outputs and sort of iteratively, like at different layers, added the original input in to sort of localize where the knowledge was being recalled. And then they ran this editing study to sort of confirm that that they had guessed right about where knowledge was stored. So so you can also so the Eleuther group has been doing this sort of, as well as the diffusion study has been doing this projection work where you sort of project onto these orthogonal subspaces. And so if you move in a direction and you're trying to edit a particular concept, but that concept is entangled with a lot of other concepts, there's a few different things that you can do where you project onto a space that is sort of linearly has no covariance with any of the concepts it's entangled with, and so you can sort of like separate stuff out like that, sort of same energy as like a Fourier transform or something like that. So you can also play around with, if you run PCA on the Jacobian of weight matrices. So Jacobians are that's the second derivative of the weight matrix. If you run PCA on that, then the directions that you find with PCA are going to be directions which have maximum that change the output maximally. And so there's sort of ideas where you can play around with doing that to make changes in specific places. Another thing that Christopher Manning's group was doing is to sort of make a set of meta networks. So neural networks whose goal is to edit other neural networks. And so the normal problem with that is that the inputs to that are the weights of another network. And so usually that's just like, it's just computationally intractable, right? Because the inputs are a set of weights and the outputs are also a set of weights, but there's just billions of weights in large networks. And so they sort of get around that by, instead of having the neural network edit the entire weight matrices, they have the neural network edit the rank one outer product of the weight matrices. And so the interesting thing there is that it turns out that still actually sort of works, especially if if you can run SVD, you can look at the rank one outer product, and because that's the matrix that has the most information about the gradient, you can just edit that matrix as in its vector form, and that will actually sort of simulate the changes that you want to make. And so then the Eleuther group, actually, I guess this is the same as this other one, but in slightly different papers. You find a subspace responsible for linear correlations between two concepts, and then you take the subspace that's orthogonal to that, and then you project onto that orthogonal subspace. And so you can sort of view that from an information theory perspective, where you find a subspace that maximizes the mutual information between two concepts, and then you find the subspace that's orthogonal to that, and that sort of works in sort of the locally linear sense. Although when you try to make edits that are too big, you sort of run into nonlinearities and it breaks down. So that's sort of a lot. I realize that that's sort of a lot of information right off the bat, but we're going to go through each of these ideas one by one, with a paper being sort of our example, and hopefully we'll get some sense of each one. So we're going to start with this interpretable diffusion paper. So this is one of the Technion group. They're working with René Haas at the University of Copenhagen. And so this is actually the only one that we'll look at that's on image editing with diffusion models. And so I think this is a great one to start at, because you can sort of see you can sort of see what you're doing directly, right? I mean, if you find a direction that's responsible for smiling, if you look over here, you can sort of move along that direction and decode, and then you'll see that the output image is unchanged except for the fact that the woman starts smiling. So they changed this. They trained this on there's a big celebrity faces data set. They trained this on. So the idea behind this paper is that so if anybody's unfamiliar, the way a diffusion model works is that you train a U-net to essentially predict noise at different time steps. So you start with a clear image, you add a little bit of noise, and you train a network to predict what that noise was, and then you add a little bit more noise, and you predict that new noise that you added, and you keep doing that until it's totally noisy, and then you can sort of reverse that process to sort of iteratively denoise into like an output that makes sense. And so there's sort of other things involved. There's a variational autoencoder that's often used to project, and so you add noise into the space created by the variational autoencoder instead. But what you can do is it turns out that the U-net has a set of the bottom of the U-net. It turns out you can create a latent space out of that, and there's a way in which that latent space is interpretable and sort of smooth. So you can move along it, and you can create sort of smooth changes in the output. And so what you do to create that is that you concatenate the so say you have an image, you run the image through the U-net, and at the bottom of the U-net, you take its activation, and then you concatenate that activation for all of the different diffusion time steps, and you say that that's your latent space. And so it turns out that you can sort of do this vector arithmetic in that latent space. So for instance, if you take a picture of somebody smiling, and then you add the difference between a guy smiling and a guy not smiling, and you can sort of scale it down appropriately. You can make a woman that smiles, but you can make it so that she's not male. So they sort of played around with that. One thing that they do is you want to be able to find reasonable directions. And so what you do is you create this matrix where you take a bunch of samples, and that are all sort of like doing the same thing, smiling or whatever. You concatenate all of those samples, and then you take and then you run PCA on that, and then the directions in PCA will generally be sort of semantically interpretable. And so you can see here that if you add one of the PCA directions, you sort of get this tilt change up top here like this. You could get this gender change here, and then if you just add random directions, then you just sort of get random changes until it sort of dissolves into breaking apart entirely. And so so for example, here you have these 4 original images. You can find a pose direction here where you move along it to change pose. A smile direction, there's sort of a gender direction where you can change the gender, and then there's an age direction that they found where you can move along this direction and increase or decrease the age of the person. And so the other thing that they want to do is say there's an image, and in the image one person has glasses, right? And so and there's a different image where there aren't any glasses that exist. And so so you might be in this situation where there are directions that are kind of particular to individual images that don't make sense for other images, right? So moving along a glasses direction wouldn't really make sense. If like, say you had an image of I don't know, like a tree, right? Moving along a glasses direction, like wouldn't really make sense for the tree, because what does that even mean to add glasses to a tree? You know what I mean? So one thing that they do is they find edits that are specific to images. And so what they do for that is that they look, so H space is their semantic direction. And so they look for directions that induce the biggest change in the predicted image at every time step. And so directions that cause the biggest change correspond to the Jacobian, right? So that's just the derivative of the gradients. And so if you take the Jacobian, you take its singular value decomposition, then you can move along, the biggest singular vectors, and you'll find, for a particular image, you'll find directions that change it the most, and then you can sort of look at those directions manually and see what they do, you can sort of learn interesting stuff from doing that. So then the other thing that often happens is that you do this sort of PCA thing, you move along a direction, and then it turns out that you are, there's multiple different semantic changes that happen, right? So you move along a PCA direction, but then, glasses get added, but then age also gets affected. And so what you can do, so this is the projection thing. So what you can do is you can concatenate these directions into a column matrix, and you can essentially like you can find one direction that's like an age direction subtracted from the glasses direction, right? And another direction that's like the age direction subtracted from the gender direction, and so on. And you can concatenate all of these subtractions into a single matrix. And then if you project onto the complement of that matrix, then you can, for each of the k directions that you care about, you can sort of disentangle it from all of the other from all of the other things that you could do. So for example, here is an original PCA direction where you move along it, and it affects both glasses and age. But then once you do this projection, you can move along it, and now you only have glasses get changed. You don't change the age. And so then you have the opposite effect over here. And so so
hey,
that's
Alex,
the diffusion. Yeah.
So sorry, I have two questions. One of them is kind of going back a little bit.
Mm-hmm.
Okay. So all of this data that you're using is coming from the bottom of the UNet.
Yeah.
Okay. And so really the left half of UNet really is just kind of like a CNN, like we're used to, just a regular, convolutional neural network. And we're kind of used to this idea that when you get to the end, that's sort of the bottleneck, and people often use that as sort of like an embedding space, a latent space for images. So I think that concept's not that unusual. My question, pretty simple one, is just, did they do anything special to try to get better embeddings from that bottleneck, or it's just no? However these models were already trained, we just took one off the shelf and grabbed the weights, and voila, that's our latent space.
Well, I think the trick is that you have a bunch of different time steps, and so how do you choose which time step which time steps latent space you use? And so their trick was just concatenating that bottleneck activations for all of the time steps, and then using that as the latent space instead. And so I think that's like their like thing that's different than like the normal thing, is like they're not just using the bottleneck activation of a single UNet. They're like concatenating the activations of all of the diffusion time steps.
Okay. I mean, that kind of makes sense to me because generally what we expect is that in there's forward and backwards, so I don't know if I call it earlier or later, but when you're generating an image, the earlier steps are the ones that do high level features. So I would expect things like what you were saying, whether the face is looking slightly to the left, directly at the camera, or to the right, that has to be sort of decided pretty early on.
Yeah, right.
And then other coarser features get decided early. But, maybe I don't know, but maybe like the shape of the eyebrows happens later. You're gonna have eyebrows, but the exact shape of them, whether they're thick, thinner, straighter, or curvier, whatever, like maybe that happens, in the middle layers. And I would suspect that the latest layer activations, the latest time steps, probably are not going to give you any of these semantic features, because the last layers are usually just doing fine details. So like you have hair, and I'm just determining the exact fine structure of the hairs. I'm not really determining what color your hair is. That was already decided. I'm not, determining whether you have straight or curly hair. That's already been decided.
Yeah, right.
Okay. So then when you go forward, thanks. So then when you go forward to what you were talking about, so you've got something entangled, and so you have this direction, and you're hoping that it changes just one thing. Like you have these PCA directions. It's not like a priori you went and said, I want to find the eyeglasses dimension. You just said, here is this direction that has a lot of variation, and I'm hoping it's something very interesting, like something interpretable and interesting, like gender, right?
Yeah.
And you're like, oh shoot, it is two things. It's both glasses and age.
Yeah, exactly.
So I didn't quite follow this explanation about how you would disentangle it.
So here, let me let's go to the paper. So what they do, so I think their explanation is right here, if I remember correctly. So consider PCA where we generate n random samples, so samples of images, and we save the bottleneck activation HT at I. So for the ith sample and the teeth time step, the activation at the bottleneck layer for each sample I at all time steps. Then we vectorize HT of I for all I. So we vectorize all of the samples.
You're just flattening it for computational convenience.
Yeah. And then we calculate the PCA. And then the editing direction is that concatenation. And so then so actually the disentanglement, I think, happens. Right. So here's where the disentanglement happens. So you have positive and negative examples of some attribute, right? So say you want like eyeglasses, right? You take a bunch of examples of people who have eyeglasses, and then you take a bunch of examples of people who don't have eyeglasses, and then you have this collection of those images, and then you can find a semantic direction with by summing all of by averaging all of the differences together of those things. And so so then the disentanglement happens where you right. So if you just have two vectors, v1 and v2, say they're semantic directions, but they're entangled. So you can define some new direction, which only affects the semantics associated with v1 by just removing from v1 the projection of v1 onto v2. So you basically just right, you have two directions, they're both entangled with each other, and then you just project out the entanglement.
But I thought you said how we got v1 was we did PCA.
Yeah.
So if you do
PCA, so they're already orthogonal.
They're already orthogonal to each other.
Oh,
so
I see what you mean.
Projection of v1. That's what kind of.
Yeah. Oh, I see what you mean. Yeah.
But if
I don't
the
know.
other
That's a
thing
good
you
question.
said though makes
I hadn't thought
sense.
about
If you just take a set of eyeglasses and no eyeglasses pictures,
Yeah.
and you find, like, I don't know how they differ on your various principal components, then maybe you can say, yeah, here's where the eyeglass seems to like really stand out.
Yeah, right. So yeah, so maybe that's what I misunderstood about this paper. So maybe that's just you find V just from doing this, and that's not doing PCA yet. And then you do the projection prior to the PCA, and then you do the PCA after. I think that actually makes more sense, because yeah, you're right. If you project PCA directions, well, that doesn't make any sense because they're already orthogonal. So yeah, so I think that's what they do.
Okay.
So yeah.
So
Thanks.
cool. So then the idea is I average a bunch of eyeglasses versus not eyeglasses pictures, and you hope that the other things like gender and hair color will cancel out. Because you just have a variety of different pictures. And so the strongest signal you hope remaining will be eyeglasses versus not eyeglasses.
Yeah, exactly. So yeah, sorry. I hope that cleared that up.
All right, thanks.
Yeah. So
is that similar to how the contrastive training works?
I think it's a little bit different. With contrastive training, what you have is you part of the loss function while you're training says that, so say you're doing contrastive training for images and text. Part of the loss function as you're training basically tries to minimize the distance in the latent space between the images and the text embeddings. And so yeah, contrastive is more about like, okay, you have two different modalities, but they represent the same thing. And we want to make sure that the internal representations in the model are as similar as possible.
Okay, thank you.
Okay, so we're running a little bit short on time pretty quickly. So I'll try to speed up a little bit. So the next paper is more Java is
by the way, we are scheduled to 1:30, not 1. So
okay, yeah.
I know you have a lot of content, and we'll see what we cover, but you're not that short on time.
Yeah. All right. So this is sort of this group at Tel Aviv University, and then the Allen Institute for AI as well. Morjiva was actually in DeepMind recently too, and she just got her professorship at Tel Aviv. So so she's been doing interpretability work for a long time, at both at Tel Aviv and then at DeepMind, and also at Allen Institute for AI. So so the idea here is essentially you create this conceptual framework where you can project the parameters of a trained transformer back into the embedding space, so the space of vocabulary items that they operate on. And so so the nice thing here is that if you do that, then you've projected into the same space that every transformer that uses that vocabulary uses. And it turns out that like a lot of different models get constructed on top of the same vocabulary. And so this is sort of a way, as I understand it, to kind of directly compare models with each other, that even if they were totally different, trained differently and everything, you can sort of project into this embedding space for all of them, and you'll you'll be able to sort of compare them one to one. And so they're
Sorry, can I stop you right there?
Yeah.
Because my understanding is that most large transformer models are trained end to end, and that the embedding is part of the end-to-end training. So then the token embedding would be unique to every training run.
I'm not sure. They do these experiments in this paper where there's they have a few different models that were trained separately, and they they kind of project them all together, and they show that it's sort of interpretable when you do that. But yeah, I'm not sure.
All right. So then I'm going to ask another question, which maybe is a dumb question, but I thought that everything that transformers do is already operating on embedding space. The residual stream is in embedding space.
Mm-hmm.
So I don't understand what projecting back to embedding space means, because I think it's, in my mind, it's already in embedding space.
Well, I think projecting back to embedding space means you have, you've kind of processed it a lot, right? Like you've run your, your set of tokens through all these transformer layers, and you've, modified them, you've modified them with the self-attention layers over and over, but that at each self-attention layer, you can project back into a common space. Like you can project using the original embedding matrix. You can sort of you can project them all so that they're in the same like original space. That was my understanding of it, at least.
Because if you use the inverse of the embedding matrix, then what you're really projecting back towards, I know you're not going to get exactly that. What you're projecting towards is the one-hot encoding.
Mm-hmm.
So is that the space they're talking about? So like for a vocabulary of 30,000, it would be a 30,000 dimensional, originally one-hot encoded space?
Yes, I think so.
Okay.
Yeah. But yeah, I mean, so the idea, I mean, we can like read their abstract, right? Or we can read the part of their introduction. Like, you can project hidden space to the embedding space via the embedding matrix. And then you can project back by multiplying with the right inverse of the embedding matrix. And so you can recast inner products in anywhere you want in the model as inner products in that embedding space. So yeah, I'm not sure if that like clears anything up or is just more confusing.
Okay, yeah, I think that's, I don't know that I'm familiar with using the terminology that way, but it does sound like they're going back to the 30,000, 50,000 dimensional token space.
Yeah, right.
That's kind of what maybe that's the wrong name, but that's kind of what I would have called it.
Yeah, I mean, they said that you can do this as long as the tokenizer is common, like as long as the tokenizer is the same. So yeah, I'm pretty sure that's what they're doing. So I mean, here, this might help a little bit too. So so you have on the left, you have the most active vocabulary items for a feed forward key and a feed forward value. So this and this, you take the top K in the embedding space and you get out a set of tokens. And then I guess you can in the middle, this is what I was talking about with this parameter alignment thing. So you can take two models, model A and model B. You can compute the dot product in embedding space between feed forward key pairs from different layers, pack them into a similarity matrix and average it. Yeah, and so this was my understanding of like how you can use this to compare model to model, but I'm not sure. Maybe I misunderstood this paper, but yeah. So
it seems to me that if you go back to the token space, then basically if one model on the residual stream says, I think the next word should be apple, and another model says, I think it should be apple, even if they have different embedding matrices, they're going to be aligned if they're both thinking apple.
Yeah.
Which, that's a good thing. makes sense that they should agree if they're agreeing on the next word. But
right.
I'm probably missing. There's probably something more to this paper, because that what I'm saying sounds somewhat trivial.
Mm-hmm.
I think maybe a piece of it is you might be able to do that at the top level where you have a given vocabulary, but then you have all of the other transformer blocks after, and maybe there's some alignment on the later layers. I think that that's part of it. I was reading the abstract a little bit, and they're saying that you can align all parameters, not just that top layer.
Mm-hmm.
Yeah, it makes sense, but like that's one of the things that I've been thinking about transformers is to what extent is the original word known and recoverable. It's actually one of the things I've been thinking about playing around with. So so if you say, you know, the quick brown fox jumps, the quick brown fox jumps, that's five words. Well, let's just say each one is its own token. Okay, so the fifth input token is jumps, and the output, when you finally go through all the layers, let's say it says the maximum logit is over, and so I'm predicting the next word is over. Okay. I've been curious to what extent, if you look at those later layers, can you extract the word jumps? Does it still know that? Because the residual stream, the work that I've seen, the what was it called? The I can't remember the name of it, but it was like the logit viewer. I'm getting the name of it wrong.
Oh yeah, the thing, the Eleuther thing. The
The original one was just like some guy not even affiliated. He just had like a GitHub, right?
Oh,
but basically what he did is he took the output matrix that gives you your logits, and he just applied it to the residual stream at every layer.
Mm-hmm.
And what was found is, except for the very early layers, that you can pretty like 80 to 90% of the time, you can already see the word that ended up being the max probability word. You can see it very early on in the layers. That it will sometimes change later on, but usually by like layer 6 or whatever, out of like, you know, 30, 40, 70 layers, that's already the max probability word.
Mm-hmm. Yeah.
Okay. But yes, I've always wondered, well, what happens if you just take the like unembedding matrix or some the inverse of the embedding matrix or something? Can you extract the original word?
Yeah. Right.
As you go further up? Because before the first layer, you have to. It'll be perfect recovery, right? Before the first transformer layer, all you have is exactly the embedded token.
Yeah.
And so it always seemed to me that there's sparsity in that space, and that it's computing the next token in sort of the empty dimensions of that embedding space.
Mm-hmm.
But I've never actually seen where somebody actually directly proved that, yeah, the original token is still there. It has not been lost while it's been doing all the calculations to figure out the next word.
Yeah. Right. Yeah. So cool. Do we want to stay on this, or do we want to move on?
Your call. That's fine. Thanks, Al.
Cool.
Thanks, Al.
Yeah. So okay. So the next paper I wanted to look at is David Bao's work on mechanistic interpretability. So David Bao he was at MIT. He graduated in 2021, and he got sort of an immediate professorship at Northeastern. And his work at MIT was sort of in this same area of sort of knowledge localization. And so this paper is sort of and Kevin Mang was his PhD student, who I think did most of this work. And so this Rome paper is sort of like his big paper in the last couple of years that sort of, I think, got a lot of kind of talk on Twitter and everything. So what they did in this paper is they essentially did this ablation study, as far as I know, where they first did like a normal forward pass through, I think, like GPT-2 or something, and then what they did is that they corrupted the output at every layer. Like they corrupted the they corrupted every layer, and then they sort of put in the original feed, the original forward passes. They like drop in and replace the original forward pass to the corrupted output, and they just sort of like did that one by one until they could like localize knowledge, is the general idea. And then they came up with this sort of like rank one model editing thing that then let them sort of confirm that that's what they were, that sort of worked. So sorry, one sec, let me plug in my iPad here. So okay, so the idea here is that what they found is that knowledge lives in rank one arrangements of neurons instead of individual neurons. And so this sort of this figure sort of explains generally what they did. So they run a forward pass once normally, and then they corrupt the subject token. So there's there's a subject, a relationship, and an object. So the subject, for instance, would be the Space Needle, right? And then the object would be downtown, and then the relationship would be is in. So so they sort of broke things apart into that sort of tuple, and then they corrupted the subject token. And so they corrupted the token for the Space Needle. They just added noise to it. And they added noise to that in every layer, and then they sort of by putting the original version back in one by one, they sort of localized where the information for that subject like was originally pulled up. So they found these two different sites. So they so here's the restored layers, right? The 0th layer up to the however many layers this is, 50 or something. And so they found two sites where the act of restoring the layer also restored the word downtown. And so they have this like early site and then this late site. I guess the late site makes sense because that's right before the output is about to happen. But then they have this this early site here as well, where if you sort of restore the corrupted output over here, then then that'll get you to reconstruct the word downtown. So yeah, so this is the idea. You run a forward pass with a sentence like the Space Needle is in downtown Seattle with a subject, relationship, and object. You corrupt the embedding of the subject token with noise, and then you run a second forward pass. You kind of restrict this to situations where the wrong output is returned. And then you start just, like I said, you just start restoring layer by layer. And then if the object output is restored by fixing a layer, then the idea is that layer has a high sort of causal importance to reconstructing the whole to the relationship. So then they sort of dove a little bit deeper into this. Okay, what about weights rather than just layers? And so the idea is that they viewed layer pairs as a key value store for a set of vectors, vector keys and vector values that you find by solving W as the weight matrix. So you can solve WK equals V to go from the embeddings of keys to the embeddings of values. So the idea here is that there's some key that represents the Space Needle, and then you solve WK equals V, with the relationship is embedded into this key in order to get this Space Needle embedding here as the output. And so so what they did, and this was sort of earlier research by actually Morjeva, same person we just looked at, sort of gave this idea that could be like a reasonable thing to do. That in feed forward layers, these object relationships are stored as key value pairs through linear transformations. So so what they did to confirm this is that they insert a new key value pair into the system by basically finding the insert that changes the weight matrix as little as possible, while still causing the that slightly changed weight matrix times the Space Needle embedding key to equal the downtown embedding key. So they just solved the least squares problem in order to find this weight matrix. And so to find this subject K star, they choose inputs that represent the subject its last token as the lookup key K star. So the way that they do this is that they pass a bunch of text containing the subject. So a bunch of different text all containing the Space Needle through G is the whole network. And then at the layer that they are editing, and at the last subject token index I, they read the value after the nonlinearity, and then they sort of average, and so that's how they sort of that's how they select the subject, and then to select the value. I didn't really fully understand this, but they select some vector that best encodes the probability of having that relationship. So R would be I think Space Needle, and O star would be is in. I didn't fully understand how they selected this this value vector, but as far as I can tell, like they just selected the one that would best cause that would best cause the key to predict it with the weight matrix, was sort of my understanding of this, but that might be that might not be a perfect understanding. The point is, at the end of the day, you have a key vector and a value vector, and then you do this edit by just doing this rank one updates that inserts the key value association. And so they just minimize this sum of squares equation such that their new weight matrix times their times the key that we found corresponds to the value that they found. And so that's how the edit there works. So anyway, so I think this paper is just, in general, it's interesting because they have this way of sort of localizing where you actually make the decision that you're going to that if you have the Space Needle and you have the is in relation, you can localize, like, how do you get from that to the word downtown. So yeah, that's that paper. And then we also have this sort of task arithmetic paper. So this is the only one that we're going to look at that uses fine tuning. And so what they do with this paper is you can essentially create a bunch of task vectors via fine tuning, and then you can use those task vectors once you've created them to you can make linear combinations of those task vectors and edit the original model, and that'll make sort of interesting changes in the original model. So and this is all, University of Washington generally. So, Ludwig Schmidt is at the UW. He's sort of big in sort of data focused AI. And then Ali Farhadi is the other PI involved here. So just looking at what they do, the idea is that you basically just take a checkpoint of frozen model weights, and then you fine tune the model on a particular task. So say you have an image model trained on, say you have an image model trained on ImageNet or whatever, but it's ImageNet minus all car pictures, right? So you train your checkpoint on ImageNet minus all pictures of cars, and then what you do is you fine tune your model on images of cars. And so then what you do is for every layer, you just subtract the fine-tuned weights from the checkpoint weights. And so the values that remain are your task vector. And so so that it's a pretty simple idea, but then what they do is you can make a lot of these task vectors, and then you can take linear combinations of them and add those linear combinations to the model. And then you can do things like, making the model a little bit better at, in situations where there might only be an analogy to some data instead of like having the actual data. So, for instance, you can, say you freeze the model and then you want to make like 10 task vectors, right? You can train all of those, downstream models in parallel, right? So you have this frozen one, you train it on cars, then you train it on, and in parallel to that, you train it on like, I don't know, dinosaur pictures, you train it on whatever else. And then you have a bunch of task vectors, and then you can, you can add all of those task vectors. And when you look at how the model performs on sort of the average of all of the downstream tasks, it turns out that the accuracy increases when you average on all of these downstream tasks. And so that's sort of interesting because it lets you sort of train a bunch of like copies of this model checkpoint in parallel, and then sort of combine them all. And it turns out that isn't horrible. Like that actually kind of it lets you increase in accuracy. So you can also add pairs of task vectors to get a single better model. So I didn't fully understand this part, but you can add task vectors from 2 tasks, and I guess it improves accuracy on both of them. And if you add 2 task vectors, you combine them and put them in the original model, then I guess that's competitive with just using 2 fine-tuned models that are specialized. So another thing that you can do, which I think is really interesting, is this linear combination thing. So this is what I mean. Say you want to create a task vector of like indoor lions, right? So you've trained on a bunch of pictures of outdoors. You've trained on a bunch of pictures of lions, but you have almost no pictures of lions that are indoor. And what you can do is you can take all of the pictures of outdoor lions, and then you can add that with the difference between dogs that are indoor and dogs that are outdoor. So you basically add the you change the lion outdoors to lion indoors by sort of this sort of linear, this addition. And and it turns out that actually sort of works. So you can sort of learn about situations where you have sort of sparse training data by doing this sort of by analogy. So that's kind of the general idea with this task vectors thing. I think the big downside is that when you have to sort of you're sort of stuck in linear space here, right? So my guess is that the actual gradient space is like super nonlinear, but you can just add a small amount of vectors linearly, and that'll kind of create changes that you like. But they didn't really mention this in the paper, but I'm assuming that if you add sort of larger magnitude versions of these vectors, you'll sort of get out of that linear space that you were originally in, and it'll start to break down. But I'm not entirely positive about that.
Did they add any pictures? Because I wonder if the lines became size of dogs.
Oh, that's a good question. I don't think so. If we look at the paper,
weren't they doing classification in this paper, not generation?
Yeah. I think, you're right. That was a classification task. Yeah. So it's not, so they don't like create any pictures of lions. It's like predicting, whether it's a dog or not from the image. And so if you have a few pictures of indoor lions, and you get better at predicting those by adding that task vector.
Yeah, so they did this with images. I think people have looked at LoRa fine-tuning of language models, and they've done stuff where they've said, hey, we did one fine-tuning, whatever, on like, well, for language it doesn't make sense. For images, I was going to say like just iPhones, because it knows what a phone is, but it doesn't actually know different models of iPhones or different models of Android phones, whatever. So for the task arithmetic, you could like sum those two fine-tuned differences, and you get a model that works well on both iPhones and Android phones, right? I can't think of a good example, but people have done it where they've done two separate fine-tuning. So let's say fine-tuning on legal terminology, fine-tuning on medical terminology using LoRa. And then with LoRa, you're just adding those LoRa weights back to the original weights, right? So you could take two different LoRas, you could add them back. And what I recall seeing is that when they've done that with LLMs, it did not work.
Oh, really?
Yeah, you did not get a model that was good at both medical and legal. You got gibberish. It degraded the performance on both.
Yeah, interesting.
I've been looking at a lot of the prompt tuning stuff, which is very related to this. And in the prompt tuning paper, they actually mention similar stuff to this, where you can actually successfully average many prompts together, and you can actually get capabilities of each of them combined and better accuracy if you retrain 10 prompts and average them together, and you can do prompt ensembling. And I'm sure that there's some that are orthogonal and cause problems with each other, but in general, they found that they can kind of create a mega prompt that does well.
Yeah. I mean, I think so. This is like a sort of related to what you said, is what they found is that when you look at cosine similarities between different task vectors, they're generally pretty close to orthogonal. Like this, they're not exactly orthogonal, but this is like, this matrix, this cosine similarity matrix is pretty close to the identity matrix, which is, it would be exactly the identity matrix if all of the task vectors were perfectly orthogonal. So I think that's a lot of the reason why you're able to do this, is that most of these task vectors are pretty orthogonal. Which I don't actually understand why they would be orthogonal. Like, it's not intuitive to me. It's like not obvious to me that creating these vectors in the way that they do would cause them to be orthogonal.
Yeah, I mean, I have two comments on that. So one comment is that I believe these are in the full weight space. So in a high dimensional space, almost all vectors are close to orthogonal. So you pick two random vectors in a 300 dimensional space, and their cosine similarity is going to be like 0.01.
Right.
So that's one reason why you see these numbers. So whether or not those numbers, 0.01, 0.02, an occasional 0.05 here or there, Whether that's lower than just 2 random vectors, I don't know. But you're not going to get values like 0.5 very often.
Yeah.
You know,
and they did have some similar cosine distances that were like, you know, non-negligible, right? Like this one, the MNIST and SVHN were.
Yep. So that's interesting because SVHN, if you guys don't know, right, that's Street View house numbers. So I believe most of the house numbers are 4 digits or less. Here in San Diego, we have some pretty large house numbers, street numbers, right? But most parts of the world, they're relatively short. So it's a lot closer to MNIST. Like you can see why it might have some overlap. And you know, there's going to be like a 1 main street in every town, you know, so there'll be a 1. But so I mean, conceptually, you can imagine why those 2 data sets are the closest of any.
Yeah, and like, you know, I mean, they say here that a lot of the data sets that are like a little bit not orthogonal, it's pretty much always when the tasks are similar to each other. So like, you know, GTSRB, this one, I guess 0.06 with SVHN and MNIST. I guess GTSRB is recognizing digits as a capability that's necessary to solve this task. I don't actually know GTSRB, but
I don't know that one. I can Google it, but I don't know that one off the top of my head.
Yeah. But what I mean, they say here that in order to solve it, you need to be able to recognize digits. Oh, it's traffic sign recognition, it looks like. So yeah, I guess with traffic signs, you need to be able to recognize digits. So their task vectors are like slightly not orthogonal, I suppose. You know, which I think that's sort of interesting. Yeah, they did. I mean, they did like learning rate studies to measure the impact of that. You know, number of training steps, how that changes cosine similarity and everything. Yeah, I thought that this is, let's see, trying to see if there's anything else that we should yeah, so their main, I think that this is the main interesting thing. You can use these to forget stuff by subtracting the task vector that you did the fine tuning on, right? So, you know, fine tune, you know, ImageNet that has a bunch of cars in it on only pictures of cars, and then subtract that from the original checkpoint. Now you have an ImageNet that's like sort of forgot about cars. You know, and then, yeah, learning the addition we talked about, and then task analogies we talked about. So yeah, I think this is sort of an interesting, I like this paper a lot because it's, you know, it might not generalize to like nonlinearities, but I think this sort of thing is a very like intuitive way to play about with editing the latent space, right? You don't have to do all these like complicated things. You can just like add vectors and right. And so that, you know, I think that's sort of just like a nice idea to be able to do that sort of thing. So anyway, so next we have model editing at scale. So I didn't spend a lot of time looking at this paper, but the general idea is that this is the one where they train sort of a meta network to be able to, and 1 second, I think my iPad almost got dark. So they train a meta network to sort of be able to predict updates that you would want to make. And so this is the one where, you know, if you're trying to predict a, you know, million parameter, the updates for a million parameter model, the input to that would be a, you know, a million parameters, and the output would also be a million parameters, right? For the weight matrix. Like say your weight matrix, say like a single weight matrix is like, I don't know, like 1,000 by 1,000 or something, right? So like the input is like that size of a matrix, and the output is also that size of a matrix. So it gets like computationally intractable pretty quickly. And so their sort of innovation here, as far as I can tell, is to, like I said at the beginning, instead of having the inputs and the outputs of the model be that like the actual weight matrix, the inputs and the outputs are like the rank 1 decomposition of that weight matrix. So my understanding is that it's just they do SVD, and then they take the outer product of the most important singular component, and then that's the thing that they learn to transform on the gradient. And so it's sort of these like low rank updates idea. Yeah, so the idea is to like kind of make local model edits that don't damage performance on unrelated outputs. And the idea here is that, you have some original model. Its prediction for who is the Prime Minister of the UK is Theresa May, right? But that's because the model was trained before Boris Johnson got elected. And so then you have this, you have this neural network where you input, I guess you input, the word Boris Johnson. You put that into this neural network, and then it spits out a, and then I guess my guess is that you input the text Boris Johnson, and then you also input the either this original network or this original text. I'm not entirely sure, but the point is that the output is the like rank 1 addition to the original model that like maximizes the probability of changing its output to be Boris Johnson instead of Theresa May. And so what you get is you get this sort of like particular edit where now the output of that specific sentence is Boris Johnson. And then they also have this section in this paper where they talk about like, okay, and like related things are also edited. So so other knowledge that's sort of related to Boris Johnson being the Prime Minister of the UK is sort of also edited in a way that doesn't necessarily affect anything else too poorly. So yeah, that's the idea with this paper. Yeah, I sort of looked at this near the end, so I didn't really I didn't go too much into detail, but I'm going to post these slides, and they'll all have paper links for all of these papers. So for more details, you can go in them. So Chris Manning at Stanford is like sort of this really important computational linguist. He's done a lot of interesting stuff. Chelsea Finn is also at Stanford. Antoine Beausolet is at EPFL in Switzerland. So, I guess they were doing some collaboration with EPFL. And then Eric Mitchell also published, some other similar papers that are sort of related to this a little bit. So, yeah. And then finally, we have the Lease paper. This is, the Jacob Steinhardt, he's at Berkeley, and then the EleutherAI people. They've been working on this in their Discord for a while, and I think Lease just got accepted to NeurIPS. And so this is sort of a general method. It's not just for neural networks as far as I can tell, but it works by preventing linear classifiers from detecting a concept while changing the representation as little as possible, measured by a bunch of different norms. And so, but it's sort of linearly, it prevents all linear classifiers. So again, the downside to a lot of these methods is that you're making these linear edits, because that's sort of like what's easy to do, onto a nonlinear manifold. So you often have to be like sort of pretty careful with the amount of editing that you're doing, because if you change it too much, you're gonna get off the manifold. So this paper was pretty dense. The general idea, as far as I can tell, is that if you have some model and you give it, say you have some model and you give it text which which, say you give it some concept Z, the outputs of that model should have significant mutual information with Z. So say you have some classifier X and it can predict Z. There should be like a high amount of mutual information between X and Z. And so, so if the classifier, so the idea is that this classifier has a lower bound, which is that, you just the function that the classifier is just a linear function, right? And that's like the lower, I guess what they say is the lower bound at predicting Z. And so they found this method where you essentially remove all of the linear information about Z in X, and then it no longer can outperform a constant. So the idea is that you have your original data, you have some concept subspace that you find, and you have some output subspace. You whiten them to make it so that they're orthogonal to each other. You project onto the output subspace, and then you unwhiten. And now you've removed all linear information about that concept. So yeah, I wasn't as sure about the details here, but that's, this is sort of like the big picture idea, is that you have some data, you whiten it, you project, and then you unwhiten, and then that, I guess deletes the concept from your model. So anyway, I know we're getting close to 1:30, so we got to wrap up, but that's sort of a very broad overview of some of the interesting papers coming out of this field. If you're interested, I also recommend looking at the Anthropic transformer circuits thread. I think they've done a lot of interesting work in there. So yeah, that's it.
Cool. Thanks, Alex. Thanks for giving us that rundown. Any questions for Alex? So let me see if I can wrap up this discussion with one question, Alex. So is there an idea that you have after kind of doing this literature review of something that you'd like to try, or you'd like to, excuse me, that you'd like to see somebody try?
Yeah, I mean, I think that I think that the using mutual information idea is a little bit underexplored. And so I think that and I also think that there's a lot of this research that's sort of restricted to a particular modality that could probably work on a lot of other modalities too. So like a lot of people in the language modeling space, sort of all of their stuff is like really focused on particularly language models, and a lot of the ideas you could also apply to vision models. So I think like being a little bit more multimodal would be interesting in this space. There was another paper that I was sort of interested in that found a board game representation of the game Othello in the weight space, and so it was sort of a very particular experiment on Othello, but I think it would be interesting to repeat that experiment for like other other representations to find similar stuff. So yeah.
Cool. All right. Thanks, Alex. Really appreciate the talk. I think we will formally wrap up the presentation here, and we have our office hours, our project discussion coming up next.
Cool.
Great. Thanks, Alex.